The ICMP packet structure is somewhat unique in the fact that it doesn't sit on top of TCP or UDP. You can't block it based on TCP port filtering or UDP port filtering. And the most common usage of ICMP is probably seen in a ping packet. When someone sends out a ping request to a target system and they get a ping reply back, it's actually an ICMP echo request that goes out and an ICMP echo reply that comes back. I've opened up a trace file called ping.pcap so we can look at the standard ICMP packet structure. After this, I'm going to take you through a really strange ICMP packet structure because we actually have something called a two-headed packet in ICMP. Here's a standard ICMP packet here. It's an echo request. We have the IP header, and in the IP header, if we scroll down to the protocol field, we'll see the protocol field value indicates that ICMP is coming up next. Now let's look at the ICMP structure. I'm going to collapse the IP area, and I'm going to look at the ICMP structure after it. There's the type field. Every ICMP packet has a type field and a code field. Some types have different codes to differentiate their purpose. But in the case of an ICMP ping packet, that's all it ever is. So the code field is set to 0. In the module where we analyze unusual ICMP traffic, I'm going to show you some communications where the code field value is set to an invalid number. In ICMP packets, we have a checksum value and we have an identifier. And this identifier is going to be used to correlate ping request packets with ping reply packets. So if a packet goes out with an identifier value of 0200, the ping that comes back should also have the same identifier value. And we can see they match up. In addition, we have a sequence number. The sequence number field can also be used to match up echo requests and echo replies. Then we have the data section, which not all ICMP packets have. In this case, it's a ping packet, so it has a data field. And the data field there is simply payload padding to make the packet long enough, and that's about it. The echo reply that comes back is a type 0, code 0. We don't use any codes in an echo reply. So those are probably the two most common ICMP packets that you're going to see. Let me take you out to the master list of all of the ICMP packets. I'm at the IANA website right now, which is the Internet Assigned Numbers Authority. I'll select Protocol Number Assignment, and then on the index line, I'll select I, and scroll down until I get to the area where I see the ICMP packet information. And here we go. There's ICMP protocol parameters. It doesn't matter which one you choose here. Both of those will take you to the same page. So I'll choose the code fields area. And here you can see the master list of types that ICMP uses, as well as the reference, the majority of which are RFC 792. There's our ping packet. It's an echo packet, type 8. And there's our ping reply packet, which is a type 0 packet. Now also in this area, you'll find that some of the ICMP packets have codes, and they use codes to differentiate amongst the different packets and the purpose of the packets. So a type 3, a destination unreachable, has all these different codes available. So we have a network unreachable, host unreachable, protocol unreachable, port unreachable. Port unreachable is one of the ones you'll find more often than not. A type 3, code 3. And that would be when you go to make a DNS query on a target system. You think it's a DNS server and it's not. If it's not a DNS server, it will respond with a type 3, code 3, destination unreachable, port unreachable message. That type 3, code 3 packet structure is a little unusual. So I want to bring up a trace file that shows that. The trace file I'm going to bring up is called ICMP-destination unreachable. Here we have a ping packet going out. The source is 10.2.10.2. The destination is 10.4.88.88. But another device has answered with a message saying that the destination is unreachable because the host is unreachable. If we look inside the packet, we can see that this is a two-headed packet. We have two IP headers in the packet. We have the actual routing header to get the ICMP packet to the target. But then after the packet says destination unreachable and host unreachable, it sends back the original IP header that caused or that triggered this ICMP response packet. So this is the original header that caused this packet to be sent on the wire. And then the specifications say that you must send out at least 8 bytes of the packet following that. So here we can see the packet that was sent out originally that forced this response was an ICMP packet. But no matter which ICMP packet type that you find on the wire, all of them will always have this type field, the code field, and the checksum field. Those are the 3 constant fields that are in all ICMP communications. In addition, in every one of those communications, you'll see in the IP header that the protocol field should be set to 1. In this module, we're first going to look at how to create an ICMP capture filter. After that, we'll look at building an ICMP display filter, and then we'll look at building an ICMP display filter that looks for specific types of ICMP traffic. So the first thing we'll do is build our capture filter. I'll select the Capture Options button. You can see I had an ICMP filter in there. And you can see the syntax. It's simply ICMP. Now if you know the syntax, you can just type it in and click Start. But if you want to create and save a capture filter for this, you'll select Capture Filter. Down here, we're going to enter a new filter name, ICMP. There's our filter string. We'll click New, and once we see it in this upper window there, now we know it will be saved if we say OK. So there's my filter, and I'll click Start. Now I'm capturing traffic on this network, and I'm going to toggle over to the DOS prompt so that I can ping some systems and create some ICMP traffic. From the DOS prompt, I'll type in ping www.packet-level.com. We can see the ICMP traffic arriving in the background. And now I'll trace route to www.packet-level.com. And at this point, we should see some additional packets arriving. Now I'm going to toggle back over to Wireshark and see what we've got so far. So we can see that all of this traffic is ICMP traffic. That's all I'm getting because I have that ICMP filter. And there's more than one type of ICMP packet that it's gathering. And the way that filter is working is based on the IP header's protocol value. So this value right here is what Wireshark is using to determine that something is ICMP traffic. Now I'm going to stop capturing at this point. And I'm going to open up a trace file. And this trace file is called Evil Program. And it has a lot of ICMP packets in there, but it has a lot of other traffic as well. So the first thing I'll do is build an ICMP display filter to view that. And then I can break it down even further and only look for certain types of packets if I wish. I'll select Open, Continue without saving because I don't need to save that trace file. And the one I want to bring up is Evil Program. This is the trace. In order to just pull all the ICMP traffic out of the trace, I'll just type in ICMP. That's all we need for the display filter. Now I'll click Apply, and I'm only looking at ICMP traffic. Now in the middle window, I'm going to collapse the IP header. I don't need to see that information, but I'm going to expand the ICMP subtrees. The first packet that I see is a router solicitation packet, and it's very easy to build a filter based on any type of ICMP traffic. I can just right mouse click and say that I want to prepare a filter based on the selected value, and that's the syntax. ICMP type equals 10. In addition, I could build a filter that looks not only for the type field but the code field. So here we see a code 3. It's a destination unreachable, port unreachable message, a type 3 code 3 message. I'll right mouse click, say that I want to prepare a filter based on the selected value, and you can see it's looking for an ICMP code 3. But what about the type number? Maybe there's another ICMP type that has a code 3. I may want to expand this by saying that it has to have a code 3 and it has to have the type 3. So now I'll select type 3, right mouse click, prepare the filter, and the selected. Now a packet has to match both sides of the operator. As always, if I like this filter, I'm going to click the filter button on the left-hand side, and I'm going to give it a name. This is an icmp, type 3, code 3. I'll say new, and now my new filter is up in the filter window. I'll say OK, and these are all my icmp destination unreachable, port unreachable packets. Very easy to do. Analyzing normal icmp traffic. This is kind of a strange module because I'm not sure if I would consider any icmp traffic normal. I don't want people to do traceroute on my network. I don't want people to be pinging around my network. I don't want to see destination unreachable, port unreachable messages on my network. I don't want to see redirection packets on my network. So it's kind of a difficult module to teach here. The best I can do is probably just to open up an icmp ping set, show you again what that looks like, and say that that might be normal as long as the source is your system. Or maybe an icmp traceroute operation, as long as that icmp traceroute operation is from your system. So you're the one that's doing it. I'll bring up an icmp traceroute trace file right now. This one is called icmp traceroute normal. I'll hit enter. Now we can identify a trace route by not only the icmp portion where we see the ping packets going out, which is the typical way an icmp trace route is run, but also if we look at the IP header and examine the time to live values in each of the packets. We can see the first packet goes out with a time to live of 1, waits for a response for approximately 4.3 seconds, doesn't get a reply, sends another packet out with a time to live of 1. Now that's this implementation of traceroute. Each different implementation of traceroute may have different timing values. Doesn't get an answer, so it asks one more time. Doesn't get an answer, then it goes on to a time to live of 2. And whenever we see these ping packets and they're incrementing by 1 each time, starting with a time to live of 1, that's the feel of a traceroute. Now, because this packet couldn't go past the second router responded and said, "I'm sorry, time to live exceeded. Time to live exceeded in transit." That's the message. I'll collapse the IP header so you can see the contents of the icmp portion. So there's the type 11, code 0, the time to live exceeded in transit. And then it spit back the original IP header and the icmp portion that triggered this packet response. So again, I would only consider this normal if you were the one that was running this on the network. If somebody else is running it, I wouldn't think it was normal. I don't want the users on the network running icmp traceroute or pinging around the network. Now, because of that, a lot of companies will go through and block icmp traffic. They'll go to the border of the company and they'll completely shut down all icmp, outbound and inbound. And I'd like to give you a warning on this before you do it. Let me take you over to the IANA page again. Here I'm back at the IANA page. And the last thing I was looking at was the destination unreachable code values. I don't mind if you cut off all of the icmp traffic as long as you check first and make sure there are no dependencies. But whatever you do, don't shut off this one, a type 3 code 4. That one may eventually bite you. This packet is required when you're communicating. Let's say you're communicating from your desk and you're going through your router and you're sending traffic across the internet. And you are sending maximum sized packets, and then you hit a link that doesn't support that maximum sized packet. The router closest to you, the router on the side before you hit this lower MTU link, will send you back an icmp destination unreachable fragmentation needed but the don't fragment bit was set message. But remember, this will only happen if the packet you are sending out has the don't fragment bit set to on. What'll happen is it will send you a message and say, fragmentation needed, but the don't fragment bit was set, and this is the MTU size I can handle. And your system will automatically drop down the MTU size in the packet and send it so it can make it through that limiting link. If you block these packets from arriving back to your hosts won't have any idea what happened, and it feels just like you've hit a black hole on the internet. So I'd highly recommend that if you're going to shut off all ICMP or be very limiting on ICMP, that you leave that one ICMP, destination unreachable, fragmentation needed, but the don't fragment bit was set, and allow that to get through your firewalls, allow it to get through your border devices. Now here's one other type of ICMP traffic that you might see on your network. It's called an ICMP redirect, and it might be normal, but it might not be normal. So let me open up a trace file called icmp redirect. Now an ICMP redirect is only sent by a router. It should only be sent by a router. When a client wants to communicate with another system and it's off of the local network, it goes and it looks at its routing tables to see if it knows how to get to that target system. If it doesn't, it says, do I know how to get to that target network? If it doesn't, it figures, do I have a default gateway? And it will send the traffic to the default gateway. If there's more than one router on the network and that default gateway knows a better way to go, that default gateway can send a packet back to the client to say, hey, I'm not the best way to go. Let me tell you which way to go on the network to get there. The client should accept that ICMP redirect packet that tells us the better way to go and put that information in the routing tables and use that from that point on whenever it's trying to get to that target. Now, here's a trace where the beginning of it is really great, but I'm going to hide part of it when things go wrong. So we'll look only at the first 4 packets. The first packet is a ping packet. Goes out on the cabling system. It's from 10.2.10.2 going out to 10.3.71.7. Now, our client's on 10.2 network and the target is on a 10.3 network. So the client sends this to the router, and we can see by the MAC address, yep, that's going to a Cisco box. Now the Cisco box knows that it's not the best way to go, so it sends a response packet, an ICMP redirect packet, to the client, saying, listen, if you want to get there, I'm not the best way to go. This is what the redirect packet looks like. It comes from the Cisco box, going back to our client, and in the ICMP portion, it's a type 5, which is a redirect, and it's a redirect for the host, for the destination host address. And then that router will tell us the IP address of the router that would be a better way to go to get off of the network. We also see that the original packet that triggered this is sent back, so it's another ICMP 2-headed packet. Now upon receiving this packet, our client should take that 10.2.99.98 address and put it in its routing tables and start using that gateway address whenever it's trying to get to 10.3.71.7. So here we see in packet number 3, our client retransmits the ICMP ping request packet, but this time it's sending it to a different Cisco interface. This is the interface for the 10.2.99.98 box that we learned about before in this packet. So now we see the client going through and sending the echo request the correct direction, and then we see an echo reply coming back through that other Cisco box. So everything looks like it worked beautifully. And that's the point of ICMP redirects. If all works well, you really shouldn't have many of these, if any at all. But it's useful in case you do have multiple routers and the default gateway is not always the best way to go. Other than that, I would probably seriously restrict ICMP traffic from roaming about on my network. It's much easier to show you bad ICMP traffic than it is to show you good ICMP traffic, because the majority of ICMP traffic that you see on the network is telling you that something is wrong. Whether somebody is hitting a target on a port that is not in use, or it's somebody that is doing a redirection on the network, not your default gateway that's doing that. Or maybe we've got a workstation that's coming up and looking for a router because something went wrong in the DHCP startup process. Or maybe even we've got somebody doing OS fingerprinting, finding out what operating system is on a target by sending a strange series of ICMP packets. The first trace I'm going to bring up is called ICMP-covert channel. And this is something you should never see on your network. And I was just lucky that I captured this one quite a while ago. But this is an ICMP echo request packet, and we can see that it's a normal ICMP ping packet except for one thing. When we look down at the payload, we can see that we don't have a recognizable signature in there like we would see from normal ping utilities. We've got actual data sitting inside of the ICMP packet, and that is something that we don't want to see. So that's an example of one thing that you'll never want to see in your ICMP communications. The next trace that I'm going to open up is called ICMP-destination unreachable. And in this trace file, we have somebody sending out an ICMP ping request, and what we've gotten back is a message saying, I'm sorry, that host you're trying to get to is unreachable. So it's not that the network on the other side is unreachable, but the host is unreachable, which means that the router that's responding tried to do an ARP for the device on the other side of the router, and that device never answered back. So the router is saying, I'm sorry, I can't get you to that host. Typically that's an ICMP reply that you'll get when the target you're going after is just one hop away. Now we'll also see another request that went out, another ICMP ping that went out on the cabling system, and another message coming back saying destination unreachable. Now throughout this section I have had colorization off, but I'm going to turn the colorization on now so you can see that destination unreachable packets are very easy to spot using the colorization. They'll come up with this black background and this bright colored foreground so that you can spot them easier. The next trace I'm going to bring up is called ICMP router solicitation. Now in this case, we have a client that's on the network, and it performs a DHCP request. It's trying to get an address from the DHCP server, trying to renew its address from the DHCP server. Now the first thing is I don't like the time column here, so I'm going to change my time column setting so that it tells me from the end of one packet to the end of the next packet how often these packets occur. So we have the client going out and trying to renew an address. It's not getting an answer from the DHCP server 10.1.0.1, so it tries again approximately, as you can see, 6 seconds later. It doesn't get an answer, so this time it goes out and it does a DHCP request to the broadcast address, seeing if any DHCP server has taken over this role. Now that packet went out 305 seconds later. No answer, it waits 6 seconds and tries again. Now it's in the process of rebinding. It's desperate. 305 seconds later, it tries one more time, and then a final last-ditch effort 6 seconds later. So it's tried its 4 times going to the broadcast address, but it hasn't received the reply that it had hoped for. We can see after that the client goes and makes a DHCP discover request. That 10.1.0.3 suddenly gives up its address and goes to an address of all zeros. Does a discover just as if it's coming on the network for the first time, and it's outside of its lease time. We see a DHCP server answer back and offer an address, but the client doesn't like that. So what we see is the client make another discover request. The reason why the client doesn't like it is because in the packet you'll see the client saying, I really want 10.1.0.3. DHCP server offers it an address. It says, well, how about 10.1.22.2? Client, no, I really want my 10.1.0.3. Finally, the client has to give up. The server makes a final offer. It says, you know what, I'm offering you 10.1.22.22.2, and that's the last one I'm going to offer you. At this point, the client has no choice but to move on and accept that address. So it makes a DHCP request. Now at this point it does a standard request, and it's requesting the IP address 10.1.22.2. The server comes back and acknowledges that and provides the client with the basic information it's going to need to run on the network. Unfortunately, the DHCP server is set up incorrectly. It gives a router address of 10.0.0.1, and that's not an address of a router on the same network as the client. The client is on network 10.1, and it expects to see a router address starting with 10.1. The client goes through its gratuitous ARP process, and it realizes there's a problem with the router setting, and the client begins to do a router solicitation. Now, this router solicitation stuff is ugly, and you shouldn't have it on your network. The idea with router solicitation was that if a router, or if a host came up and didn't have a router setting, it could broadcast, or excuse me, multicast these router solicitation messages on the network. This is the multicast address for all routers on the network. And some router would hear this and send out a router advertisement, and the client would dynamically set its default gateway setting to the router that answered. In this case, there are no routers that are set up to respond with a router advertisement, so the client just keeps sending router solicitation messages 3 times till the client gives up. And at this point, the client has no default gateway, no way of getting off of its network. There is not a single point where you'll see a router solicitation is normal on a network. Hopefully you won't have these packets on the network. The router solicitation packets are a type 10 packet and a code 0. The code field is not in use, but they'll always be an icmp type 10. You can right mouse click and easily create a filter based on that value. Now the next trace I'm going to open is called OS fingerprinting. And this trace file shows a series of packets that you should never see on your network. And when you see them in this specific order, there's something going on here, and it's called OS fingerprinting. It usually precludes an attack, or it might be used by some sort of a management device to draw those pretty pictures of Linux boxes on your network and to recognize that there's a Novell box on your network or a Microsoft box. Here we can see in this trace, in packet number 11, we have a timestamp request packet that goes out. 10.0.0.29 is sending this timestamp request packet out, and it gets a reply. We see another timestamp request and another timestamp reply. Then we see an address mask request go out. No answer. Another request goes out, and then we see an information request go out. No answer, and another information request goes out. Let me scroll back up. There we go. So there's this weird series of icmp packets. Now, OS fingerprinting is the process of trying to find out what operating system is on a target. And if somebody is doing an OS-specific attack on your machines, they might do OS fingerprinting to lead it off. There really is no other reason to do OS fingerprinting on the cabling system. The timestamp request packet that goes out is a type 13. An address mask request is a type 17. And an information request is a type 15. Now, if you were ever to see just a timestamp request out on the cabling system, it might be that somebody really is trying to find out what time is on your system. Why? Why should anybody try to find out the time on your system? Anything having to do with time should probably be NTP, Network Time Protocol, where people are trying to time sync their systems, but they shouldn't be asking each other for the time. So we can build a filter to look for these specific packets. So I'm going to highlight packet number 11, which is a timestamp request. I'm going to select the type line, right mouse click, prepare this as a filter based on the selected value. Then I'm going to go down to the address mask request, the type 17 line, right mouse click, prepare this as a filter, and this time I'm going to OR the selection together. So a packet that has a type 13 or a type 17 packet would be captured in the trace. And then the last one is the information request. I'm going to highlight the line that's the type 15, right mouse click, prepare the filter, and OR them together. And this is my nice filter. If I apply this filter and I see all these packets right in a row, I know it's OS fingerprinting. So I'll apply this to this trace, and there we can see, there's the pattern, timestamp request, address mask request, and information request. Now when we see things like this where it's just timestamp requests, it feels like somebody is just actually trying to get the time on another system. But if you see them bundled together with address mask and information, then we've got to figure that they probably are trying to do OS fingerprinting. So as I said before, most ICMP traffic is not welcome on the network. Most of the time it indicates that we've got a problem. So watch your ICMP traffic. It's one of the first things that I do when I perform an on-site. I look for all the underlying ICMP traffic on the network to try to figure out if there are misconfigurations, scannings, redirections, anything like that.